Good. So I don't have material for a full lecture, so you can already think about questions that you might have towards the end of the lecture. So I just wanted to resume where we left it yesterday. So we basically talked about structured prediction, trying to model it by generalizing support vector machines with like standard hinge laws, soft margin, and we. Oh, you had this nice pointer yesterday.
Oh, you mean the laser pointer? Okay.
So we basically we ended up with this formulation where we have a quadratic objective with our weight vector. Yeah, that's fine. And yeah.
Might be switched off. That might be the batteries empty. I got a problem with this instead. Yeah, batteries empty.
Okay. And so basically the main challenge for solving these types of problems is just the large number of constraints that we have to deal with, because we effectively, if we think of the problem as a quadratic program, we get one constraint for each combination of data point and possible output. Thank you, Philip. So then we looked at a number of approaches to solve this. So we had this successive strengthening approach that we talked about, where basically we select one constraint at a time, producing better and better approximations to the QP that we want to solve. We talked about an improved way of doing this, where basically instead of looking at individual constraints, we would try to find kind of an average constraint or a summed constraint. So basically what you see here is, right, before the inside of the sum you would have what would correspond to an individual constraint, but now you're saying instead of meeting each constraint individually, what if at least we would meet them kind of on average? The idea being that thereby we can maybe make more progress by just adding a single constraint that now depends on all data points effectively. And so that was the strategy with this improved cutting plane algorithm. And I also told you that indeed that would result in quite some computational advantage. And then I think where we left it last time was we briefly talked about an alternative way of solving the problem, where we would say, instead of taking explicitly creating linear constraints out of each possible output, what if we would leave it as an unconstrained problem, where we then would have a non-smooth function which is only piecewise linear in that term here, and then apply a generalized version of maybe gradient descent, which is called subgradient descent, to that problem. And so and what we saw there is if we want to do that, and one way of doing that would be also one where we require, where we always come back to this question of what we called an oracle, separation oracle, of identifying an output that produces the maximum margin, so to speak, the maximum violation kind of the margin, and making that, in this case, this would become part of the subgradient that we are pursuing. So I would like to continue there with, yeah, that's not connected this time, with another, let me just put this here, with another algorithm that is kind of relatively new, well, not the basic algorithm that is used, that is old, that's from the 50s, but which is to apply this for structured SVMs, and this is actually being presented at ICML this year, so I'll talk a little bit about that. So one nice approach, so this is called the Frank-Wolfe algorithm, and we would like to apply this to our problem. So the Frank-Wolfe algorithm in general works as follows. It's a method to deal with quadratic programming. And what you do is you work through an iteration where you produce a sequence of solutions that hopefully converges towards the optimum. And you do it in the following way. You compute a new iterate from some old iterate by basically a convex combination of the old value and the new value. And the way you determine the new value is that you look at the current iterate, you approximate the quadratic objective by a linear objective, and then you find the corner point of your domain that minimizes that linearized objective. Okay, so I come back to this. Let me just move forward here with this wonderful sketch of mine. See, is that readable? Yes. So imagine that this is your domain, okay, that you're optimizing over. So let's say you have, 3 linear constraints here. Here's your current iterate, and here is like, let's say, this models the objective function. So the objective function kind of goes down here. So you could, right, possibly, if you did just gradient descent, let's say, you would possibly move in that direction. Now in the Frank-Wolf algorithm, you create a linearized version of your objective functions like this, right? So the isolines, and basically you determine the corner point that really minimizes the linearized objective, and then basically from here you would move in the direction of that corner. Okay, so it's very simple, but it has a few nice properties. So one is that it's linear. So basically, right, although you optimize a quadratic objective, at any iteration you only deal with the linearization of that, right? So you solve a sequence of linear problems. It has some sparseness advantages because if you select a corner, right, a corner point, and you do now whatever, a certain number of iterations, then you know that the solution, because it's just a convex combination, right, over these iterations, the final solution can be written as a linear combination over kind of the corner points that you picked, right? It'll be in the convex hull of the corner points that you picked. So the idea is if you have a polytope, let's say, that is very, very large, has many, many corners, but you only made a certain number of iterations and you've only really selected a much smaller number of corners, that your solution is representable over those corners that you've selected, right? So this is quite a key observation here. So which would actually, right, if you would just move not towards the corner but towards, let's say, any other point here, let's say you would just follow the gradient and do some line search on that or something like that, it wouldn't be clear that you maintain a sparse solution, right? Because maybe then that point, that update direction that you take, right, it might just not be representable, or all the update directions that then over time you take might just not be representable in any more compact form than maybe a convex combination of everything, which in our case is typically too large. Another advantage is that it is projection free. So because you kind of take a step towards the corner, you never overshoot. You kind of know with this eta, right, the worst I could do, or the most aggressive update would be one where I just move into that corner and everything else will be along the way towards the corner, right? So I will never leave my feasibility region, so I don't need a projection operator or something like that, which if you do, for instance, a gradient descent for a constrained problem, right? You might know that often what you do is you just implement an ordinary gradient descent, and whenever you leave your feasibility region, you project back to the feasibility region. That is not very elegant, but that is typically what's done. But now here in the Frank-Wolf algorithm, you don't need that, which is kind of nice. And the learning rate, also, as we will see, there's one appealing thing that often the optimal step size can be computed analytically, or it can be found via line search, so that also has some nice properties. And then there's also, I will not talk much about that, but you can see that in the paper. There's also a nice way of looking at what's called the duality gap, in our case, to basically be smarter about termination criterion for the algorithm. So this is by, you can see the reference in the paper, Simon, Lacoste-Julien, and a number of authors. So here is also the much more fancy 3D slide again, so that you really understand the basic idea behind the Frank-Wolf algorithm. So this is, let's say, your quadratic objective. There's the current iterate would be somewhere here. You compute the linearization, right, which would be, let's say, f at that point, and then the usual like Taylor approximation. So you compute the tangent at that point, and you would then look for the minimum over. So here, this M is your domain, right? You look for all corner points, and you find the one that gives you the lowest value. And you can actually already see that. Sometimes you might actually, even by making such an update step, it's completely feasible that actually you get something that was worse than before, according to the with regard to the original quadratic objective. But still, there's very nice convergence proof and analysis of convergence rate for this algorithm. So let's try to apply this to our problem, which is like a fairly generic problem. So this is the formulation, and we will, okay, I should also say we will, yes? Yeah. No, it would find along this line. The new iterate would be along this line. So maybe it would be here, right? Yes. Well, you never move all the way out to the corner, right? It's the convex combination. So it's the old iterate 1 minus eta times the optimal corner, right? And of course that rate will go down over time, right? Either you can choose a fixed schedule, and some of the analysis works with a fixed schedule, like 1 over t, right? Eta scaling with 1 over t. Or you actually compute the optimal step size, but also then once you approach kind of the optimum, right, then you will realize that you better not make any big steps away from it, right? So we will now actually apply this, or let's try to apply this to the dual version of our SVM struct problem. But maybe you have another quadratic program. You can also try to apply it to that, because you know this QP is fairly generic. So this is the dual version that we derived yesterday. So there's basically the quadratic part here, the linear part that depends on this loss function between the correct output and the incorrect output. The constraints on alpha were that in this formulation that alpha should, let's say, for each data point, we would have a probability mass function. So all the alphas are non-negative, and there's certain summation constraints that we wanted to be fulfilled. Okay, so if we look at the gradient for that, obviously we get this quadratic part here, and then we get simply that linear part, right? And so then we can also look at now what would the linearization be, because that's what we would need for the Frank-Wolf algorithm. So we would need to compute a linearization around a given point, let's say alpha star. Of this. So we would basically have the value at alpha star times the gradient and the difference vector between alpha and alpha star. So this would just be the Taylor approximation, and that we know is a lower bound on the true value because of the convexity of H. And so then we would take that would be the linearization. So you can kind of plug that already in here if you like. And then we would need to perform a minimization over the corner points, right? So what would that mean? So here is now what, if we apply this algorithm to really our structured prediction problem, how it would look like. So we plug in the gradient here. I've eliminated some constant terms. So you put that in here, and basically you get this matrix Q that contains all these joint feature vectors, right? They are all summarized in this matrix Q, so this is where all your data goes. You have the corner point that you look for, so that is a unit vector of some sort. I should say it's a unit vector. It's actually a unit stacked unit vectors for each data point, for each training point. You kind of have a unit vector, and that's actually everything stacked together, if you like, because also alpha, right? We have one parameter for each combination of training point and possible output, right? So we have n times m such parameters. So this would basically be selecting a particular y prime for each training point. And then you have this q alpha here, and you have that part, obviously. And where here, right, you get this by the inner product of this, all the loss function values that you have, and dependent on what corner you decide you want to move in, you basically just pick out specific value here. So you can see what that is. It's basically the sum over all training points of the loss between the correct output for that training point and the one that you've chosen, which is part of the corner point that you're picking here, right? So the corner point is determined by which possible outputs you're choosing. You're choosing one output for each training instance, and that defines a corner in our domain. Right, so then you plug that in here, and what that is basically through the KKT conditions, we know that this is actually just our weight vector, so we can interpret that just as our weight vector if alpha, you know, in the end would be the optimal dual parameter value. So then, and if you plug in what Q is, then you basically get this inner product here. So what have you done then? So if we look at what we have arrived at, right, this is now exactly the margin condition that we've been using before for the cutting plane algorithm and what we call the separation oracle. Because what we have here is really just our margin. So it's basically this difference vector on the correct output and the incorrect output, and here you have the actual loss function value of the output that you've picked, right? And so, since for the Frank-Wolf algorithm, we would now need to actually choose a particular corner point that minimizes that. Sorry, there should actually be. I'm missing a minus here somewhere. Sorry about that. So we would actually then pick a corner point that minimizes the linearized version. So then what we should do, if sorry for the sign problem there, effectively it should amount to computing the argmax of this expression there, which is just what our separation oracle does, right? So what does that mean? It actually means that if you apply this idea of the Frank-Wolf algorithm to the dual SVM struct problem, that it would tell you pick a particular corner point. A corner point corresponds to a combination of picking one output for each of the training instances, and we should pick that output exactly as the one that maximizes this, right? So how would you determine it? You would basically run your oracle. It would tell you on training instance 1, here is the output that the separation oracle gives you that maximizes that on training point 2, 3, and so on and so forth. And that whole combination of n possible outputs you look at, and that is what defines your corner point. And then you make a step in that direction. Okay, so, but that means actually that if you look at this expression here, if we just go back to the subgradient method, that effectively we are moving in the same update direction as we did here, right? Because this is exactly basically giving you. You can see that this is effectively giving you the same as what we then get here in terms of the update direction that we are choosing. Yeah, we can see that. Sorry about that. Yeah, actually. Yeah, it's actually not. It's not maybe as trivial directly to see in the notation that I've chosen here, but it really because this is in the dual and the subgradient method that I've described works in the primal. But it basically works out if you go back from this dual update of the alpha parameters and you compute what that means for your weight vector, you will actually see that you get something that is exactly equivalent to the subgradient method in terms of the direction. Okay, so it means that this type of update that we do, that here we basically just recover the same update direction. We've derived it in the dual through just a different mechanism, right? In the subgradient method, we would say, okay, let's look at the primal, not even roll out the constraints as a QP, but leave it as a non-differentiable convex optimization problem. And let's see that we find a subgradient for us to make an update step. And here we've gone through the dual, applied the Frank-Wolfe algorithm, and then basically we find an update scheme that effectively, if we look at it in the primal again, gives us the same direction. But it has several advantages relative to the subgradient method. You can, in terms of the step size, in the primal, if you just look at the primal, you have no idea like how far you can really go. I mean, if I give you that, right, it's like a gradient descent method, I give you that subgradient, it's not clear like how far you should really go in the primal. Here, if you look at the dual, right, you know that you have defined like a clear feasibility region, and you know that you shouldn't overshoot, for instance, by going beyond the corner, and you also can actually really optimize over a finite range of possible step sizes and come up with an optimal step size. You can look at things like duality gap because you have a primal and dual view, whereas in the subgradient method you would never worry about thinking about it in terms of a dual. It is also very similar to the cutting plane algorithm because effectively also in the cutting plane algorithm, in this improved version that we talked about, we would run the separation oracle for each training point and find the currently most violated output and then add that as a constraint, right, to our problem. This is actually equivalent because in the dual, if we add a particular constraint to our primal problem, it means that we activate certain variables that have been clamped to 0 before in the dual and now allow optimization over those. So that's equivalent because you can think of, right, the solution of the dual, so you have this polytope with lots of corners and each corner corresponds to one of the parameters. And what you do in the Frank-Wolfe algorithm is you enforce some sparseness because you always pick a corner at a time. So then the solution that you maintain, right, will always be in the convex hull of these corners. And that is just the dual view of the successive strengthening approach where you keep adding constraints to the primal, right? And with every constraint that you add, effectively you have a Lagrange parameter that in the dual gives you a degree of freedom over which you optimize. Right, so these things are actually very much related. Here, though, in the Frank-Wolfe algorithm, you would do just an incremental update size and you would not re-optimize all the other parameters that you have, right? So in the cutting plane algorithm, you would add a few more constraints or one of this like mega constraint, this big constraint, and then you would re-optimize the QP in the primal. Here, you would basically select another variable corresponding to that corner point, and you would now find the optimal value for that single variable, but you leave all the other variables that you have unchanged. Okay, so you do a coordinate descent, if you like. Right, so the picture looks, again, let's say we have like an exponential number of corners. In every step, I pick a corner, it corresponds to one parameter, right? I make an update step, choosing the optimal value of that given all the rest, and then I pick another corner, I make again an optimal update for that parameter given everything else, but I don't re-optimize over everything else. I might just reselect the same corner again maybe, and then recompute that value. So instead of doing what's also known as a fully corrective Frank-Wolfe algorithm, so you could also do that, you could think of doing it more incrementally. So that means instead of having to solve a QP, you really only have to solve this for this single number, right, in every step that you do. So you have an oracle call, you optimize this single number, you do another set of oracle calls, you optimize that number, and you just alternate that. So it's also in terms of the analysis, I won't go deep into the convergence rate analysis and whatnot. I find it's very clean and simple, a nice way of proving these rates compared to like other methods that are out there. And you can also derive a per instance version that I will look at in a second. So yeah, so if you look at what this actually does for us back in the primal, right? This is what I tried to do like earlier. Maybe I can achieve it here. It's basically what you effectively compute through this Frank-Wolfe dual is the update direction, which corresponds to this expression here. And this is also some bookkeeping you can do with the loss function. And then in the primal, your updates would just read as follows. Your new weight vector is your old weight vector with some decay plus a correction step in the direction of this here, right? And the way this y hats are chosen is exactly the corner that is given to you by the separation oracle call, okay? So, so that now looks a little bit more like the subgradient method, where this direction here, this W bar, right, would effectively be the subgradient that you've chosen. And so that achieves a conversion rate that is 1 over epsilon. If that's focusing on epsilon here as one of the critical parameters, epsilon is our approximation guarantee, the tolerance that we are willing to allow for. Okay. Any questions on this? Yeah.
Mm-hmm. Right, and so what you're doing here, you're taking this slice, which is a tangent to your actual convex function that could be
yes.
Not strictly convex, right?
Yes. At the current iterate, yes.
And then you're taking a step in the direction of the minimal corner. So you're only, where you have multiple, it's not a square, so you can have multiple corners?
Yes, of course. A corner is, so a corner in the setting here, right, is a combination of outputs. If I choose one output for every possible instance that I have, and I have n training instances, right, and then that would correspond to a corner in this setting here. Okay, maybe I should just use the board and try to explain that, okay? So what we have, what our alpha is, right, our alpha is really a matrix or a vector of parameters, right? Each of where I goes from 1 through n, so this is for each training point that we have. And y is a member of our output space, which we said, right, the cardinality of that would actually be m, right? So this we said in general is very large because, you know, of the combinatorics of the possible outputs that we could be talking about, right? And we also have this constraint, of course, this is that it is non-negative, that it is non-negative. And then also we have these normalization or box constraints, and I've assumed here that what we will have is that the sum over y of alpha iy actually equals 1. So we talked about that last time, that we can think of it as kind of probabilities for each I define, if you like, a probability mass function over the possible outputs. Right? Now, so these are our constraints, right? So what are the corner points of the polytope for these constraints, right? What are like the extreme solutions, if you like? The extreme solutions are the ones where I pick alpha, let's say, iy to be 1 for a particular y, right? For each I pick a particular choice y, and that will define a corner point of my polytope, right? These are the corner points. So for instance, a feasible, let's assume that m would be 3, so we have 3 possible outputs and we have 2 data points, right? Then alpha would effectively be, I would have 6 numbers, right? Alpha 1, 1, alpha 1, 2, alpha 1, 3, no. I said, okay, 2, 1, alpha 2, 2, alpha 3, 1, alpha 3, 2. Okay. And I would have the constraint that, for instance, alpha 1, 1 plus alpha 1, 2 should be 1, right? Alpha 2, 1 plus alpha 2, 2 should be 1. Alpha 3, 1, alpha 3, 2 should be 1. They should all be non-negative. And now the corner points for the polytope that is defined by these linear equalities and this inequality, right? Because this is just it's just a probability simplex, right? For alpha, right? So for each, the first index, right? If I just look at the first index, I have a probability simplex. For the second, I have a probability simplex. So I have a factored structure of probability simplices. And so each of these simplices will then look like this, right? It will be, let's say, alpha 1, 1 here, alpha 1, 2. I mean, here now, maybe I've chosen it the wrong way around, right? It's not so interesting. But let's say we had 3 possible outputs, right? And that would kind of be the space. And the corner points would be defined as the points where these guys actually are 1, and the other 2, let's say, are 0, right? So we should think of that as being embedded, right, in our as a probability simplex in the 3D space, right? So, or another way to think about it, right? If you have a probability mass function over m elements, right, then every probability mass function can be described as a linear combination of probability mass functions that put all the mass on just one point of my finite space, right? And that tells you that, right, all probability mass functions are convex combinations of those that put all the mass on one point. So these are the corner points, right? Now it could still be that some of these are not actually corners, but you can convince yourself that none of them is actually a convex combination of anything else, right? So, right, so I think that was a very good question to go through. So then the corner points, because my domain, right, my constraints are really so simple, are basically just these simplex constraints. I kind of know what the corner points are, right? And the corner point, again, it basically means that if I select, let's say, this variable here and this one here and this one, right, as maybe that defines a corner, maybe that defines the corner that I'm looking for in this Frank-Wolfer algorithm. What it then effectively means that in my optimization, I will change alpha 1, 1, alpha 2, 2, and alpha 3, 2. I will now change just these 3 parameters because I move towards the corner that is defined, right? The corner that I then choose effectively is one where I have a 1 here, 0, 0, 1, 0, and 1, right? So if I move in that direction and I have some learning rate that I allow myself, right, then I'm effectively changing, right? I'm effectively changing these variables that kind of correspond to the corner that I've chosen, right? So in the simplest case, assume that they've all been 0 before, right? That then means that suddenly I can augment my solution by a number of additional variables that correspond to this corner point, and now I have additional degrees of freedom, and obviously potentially I can also then find a better solution. Does that make it somewhat clearer what we have here? Yeah. Right. So I mean, for problems where you don't really understand your domain, right, and what the corners are and so on and so forth, obviously then that is less attractive. But in our case, it's kind of almost trivial to know what these corners are. Now the optimization, of course, of finding the corner that we really want to move towards, that is somewhat harder, right? Because again, that involves the oracle call, and that can maybe be computationally a hard problem of really doing this argmax. Okay, right. So then it's basically this this update direction here, right? You can see it depends on this yi hat, and this hat is what kind of the oracle does, right? So for each point, each training point, I pick an output. So that combination defines a corner point, and once I translate the update step, this update direction back into the primal space, it actually turns out that it is simply a linear combination of these feature vectors that we call delta psi for the ith training example that defines my update direction, right? Okay, so here's also the picture that I tried to draw here, because if you want to think about maybe of how to do this not in this joint setting, but for individual training, one training point at a time, then you can also do what is called a block coordinate version of the Frank-Wolfe algorithm. And the reason that that is appealing is, again, we talked about that before, but the constraint structure really factorizes nicely over my training instances, right? So there's no coupling between different training instances. Only the parameters that belong to the same training instance are coupled through this normalization constraint. So then what I can also do is basically think of this Frank-Wolfe algorithm in the way that I only pick one training example at a time. The best way to do this is actually to just randomly pick one at a time, to basically freeze all the other parameters, all the other alpha parameters that are, you know, alpha I, something that are where I is not equal to the one that I've chosen. I won't touch those. But then to basically find the optimal point in this much smaller simplex, which means now I have to call just the oracle once, just for that point, to give me the optimal corner, as we've seen that corresponds to solving the linearization, that is equivalent. And then I make an update step in that direction. And then I pick another training point, and I determine a corner through an oracle call, and I make an update step in that direction. And so that gives you a way of basically coming back to the very first method that we talked about, where really you combine one oracle call, one update step, and you alternate that. So if you look at the ICML paper, you can also see that there's a comparison on like a few data sets of the scalability of these methods. In particular, also this block coordinate version of Frank-Wolfe is one that gives you very good results relative to subgradient methods, to cutting plane methods, and the pure batch version of the Frank-Wolfe algorithm also gives you like comparable to the others. So I think that is very nice. It's for me it's a very promising approach. I see like some potential, like one of the caveats of this method currently that I think requires a bit more work is that if you want to think it back in the primal, that what you actually need to keep as bookkeeping is you need to store one weight vector effectively per training instance if you want to apply this primal dual version, because basically you need to remember which corners you've kind of visited for each training instance. And so in order to do that effectively on the primal, you would need to store one weight vector per training point. So that actually means that in practice, if you have lots of training examples, you cannot, this primal dual version is not very attractive, because effectively, right, you would just have to multiply your weight vectors quite a bit. You can of course still do it in the dual if you want, right? There you just keep these variables around, but this version that translates it back into the primal is more problematic. But so this today I think is the fastest algorithm that's out there for this problem. Okay, any other questions on that? Okay, so then let me talk about one more method before I look at approaches that exploit decompositions of our function. So another way that, so like one point of criticism for all these methods usually is that, well, you know, you need the separation oracle, like, you know, how are you going to implement that? Maybe there's an exact solution and you look for epsilon approximate solutions, so that seems not very elegant and, you know, principle to do. So maybe you can also try to, if there are cases that are tractable, to more directly approach those, and maybe you can even derive other approximations along the way. So one way to think about this is the following, is cases where the selection of the constraint or the direction, which comes through this maximization problem here, where that problem can be rewritten itself, let's say, as a linear program. Okay, so imagine that in order to compute that, I can make a change of variables, and this is just, right, just placeholders, and I don't tell you how any of those relates to any of the things above, right? But structurally speaking, if you could formulate an equivalent linear problem with new variables, so that if you would maximize over these vector valued variables, let's say z here, okay, and here we have these z's being multiplied with things that are linear transformations of our original weight vector, let's say, and there's some constant term here and there. But if you could do that, right, then you would actually have a nested optimization problem, right, within our quadratic program, right? So we would have our quadratic program, and we take the constraints the way we did it with the subgradient methods and actually fold it back into the objective. So basically have an unconstrained problem. But the selection problem, this maximization problem that we had to do, let's say, in a subgradient method, we now actually introduce new variables explicitly that solve that maximization problem. So then what you get effectively is a problem that then would look like this, right? It would be a problem where we minimize over our weights. So this is as before, and we have this, you know, Euclidean norm of the weight vector. That's all fine, and we have things that come from our you know, this just constant here. And then we would have the part that would actually implicitly define which constraints is kind of active for a given W, right? And we would do that implicitly over a maximization of over these new variables C. So this is also a possibility for some methods. So if we look at, for a specific example, just to make that a little bit clearer, how you could do this. So imagine that, so we talked about alignment problems and the like, where I compute some kind of alignment or matching. So let's look at the simplest case of maybe where the output that I want to produce is a bipartite matching of some sort. So, so I would have some node set, and I have something on the left side, the source and the target node, let's say, and all the edges would go from the source to the target. And I would represent the alignment between nodes on the left and on the right through binary variables, yjk, such that yjk being 1 would indicate that the node j on the left-hand side is aligned or matched with node k on the right-hand side. Okay, so obviously I would need to enforce certain constraints. And I can do that, but also I move to a view where I actually relax the integrality constraint on these y's, and I introduce variables z's that are just the y's, but they can be between 0 and 1 and not necessarily just either or. So then what I need to enforce is that there's only, each k is only matched to one possible j, and each j is only matched to at maximum one possible k. So that would include the case where some nodes are not matched at all, but each node that is matched needs to be matched with one unique node on the other side. So you would enforce that, and here would be basically a term that comes from the matching scores that you define, and then what, you know, adding up the scores for all the edges that you've chosen to include in your matching or your alignment. Okay, so this is a relaxation of an integer program which would compute the optimal matching, right? So I would try to maximize that, get scores as high as possible through my matching, and making sure that what I have is really a matching. Now, the interesting thing is, for the matching problem, for instance, if you look at the relaxed version of the problem, that it is known that this linear program will lead, if you solve it, to solutions that are integral. So although you worked in a relaxation, the optimum of that program is actually an integral solution. So you can recover the true the truly optimal y's from the linear program, you don't have to do any rounding or things like that for that specific problem. For others, maybe you have to do rounding. Right? So now what that means is that if I want to learn, like given some input, let's say, right, as 2 strings, and I want to learn the optimal alignment, and I have some function that measures like features of the alignment, and I have training data that tells me for some examples what the optimal alignment is, that I can formulate all that alignment problem in through this linear program and then basically integrate it into my optimization problem, right? So then I get this saddle point problem, right? Oops, as I said here, right? So it'll be then of that form. And then there's basically, you basically look around of like how you can solve these type of saddle point problems, because of course now you have a min and a max, right? So you can either try to convert that maximization problem into a minimization problem by looking at maybe the dual program of that, or you can apply, and this was suggested in a paper by Ben Tashkar and others, you can apply what's known as the extra gradient method that allows you to solve these type of saddle point problems, right? So then effectively the z variables, if you like, they always capture like what are the currently relevant constraints, what are the alignments that you should actually currently consider, and the outer optimization over W is basically just doing what it always has been doing before. So that's also a nice way that you can solve problems like that. You need, of course, then to make much more specific assumptions about what is your output space, what type of problem are you solving, and can this oracle-based approach effectively be represented as a little linear program inside of our QP, and then you can solve that combined problem. Okay, so then I would like to talk to the last part. So if you're a little bit lost with all this stuff, because I'm not explaining well, and yesterday the memory is already erased of what I talked about yesterday, and the food was too good and the sun was too bright, then maybe you can try to catch up again on this very last stretch that I will take you through, which is a little bit separate from the rest, which deals with decomposition-based algorithms. So in all the things that we've done so far, right, with exception of this very last thing, we've never actually asked ourselves what these outputs really look like. I always said, like, we extract some features, and then we just work in that feature representation, and we need kind of this oracle, but we never actually worried much about like what specific problems. And so sometimes, though, it can be very useful to think more about, okay, I have a structured prediction problem, but what type of structures am I actually talking about? And of course, a very nice framework for modeling structures and dependencies of variables that are related in certain ways are graphical models. And in particular, what I will just allude here to is factor graphs. Okay, so very often for our structured output problems, what we will see is a situation where, okay, we want to define a function f like this, which scores for a given input a possible output y. But in reality, the way we want to maybe design this is by defining certain factors c. Okay, so this could be, if you like, in a Markov network, maybe this is a clique. You can think of it as that, so or some part of your output, and we would look at that part or that factor and have a function that restricts x to certain variables that are relevant for that factor, and also the y part to certain variables that are relevant for that factor, and then just have a function that assesses how well that part of the input and that part of the output, how compatible they are, how you would score them, and then the overall score. Right, you would actually basically put together just by additively combining this. So for instance, if you have a hidden Markov model or something like that, right, then you have a specific observation that you would like to associate typically with a particular state in the chain, right? So you would look at that specific y variable and that specific input, and not like all the other inputs maybe, right? So then that would, for instance, be a factor. Like at a given time step t, the latent class variable and the observed output together, that could form such a factor, right? Or two neighboring labels, that could be another factor. So basically the idea is you break down this global function into smaller pieces, sums of functions that are defined over these smaller pieces. And like one way you can actually do this in the linear part is of course also by defining the feature function in a way that the features actually split up in a certain way, so that you look at a particular aspect of your output, a particular subset of variables, let's say, and extract features from that. So if you think about these C's corresponding to cliques, you could, for instance, capture what value the variables have that are in that clique. And so each possible value could be a feature of its own, let's say. You could do things like that. Okay. And then algebraically, you can see, like, if you would define also your feature function like that and you just plug it in, you see that effectively what you're getting is also exactly this form here, right? So this is a typical way that you could do this in the linear case by just basically taking our joint feature function and defining these smaller factor-based feature functions and adding those up. We typically require, and there was a question like yesterday, also that the loss function decomposes into the same parts, because if it doesn't, then a lot of the math does not go through the way we usually want it to. And this is typically, but also a very natural way to think about it. So I extract the features from these factors. So I also usually have a loss function that I can maybe define in terms of these factor contributions. Okay. So if you do that, then to take out like the bigger gun here of a representer theorem to motivate this, right? Then it can actually be shown that the solution for like the typical, right, convex problems with regularization and so on and so forth, like we had like yesterday, the solution can be written in a different way that is much more compact than what the representer theorem in the general form, where we don't assume any factorization, gives us. Namely, we would get a representation as sum over the training points, right? Sum over the sample points, sum over the factors that we have, and then a sum over possible values that our variables can take within that factor. Okay, so Z is a particular variable instantiation of factor indexed by C. And then we will have some linear, some coefficient in that linear combination. And then here we will have basically our feature functions as they are defined over factors. And you can also think of them as little kernel functions that are now defined over like pieces of my output and input. Okay. And of course the cardinality of this, so this is like in graphical models, right? If you think of these as being cliques, then this here is actually the clique size, right? So the number of variables is kind of just the sum of the clique sizes, so it's dominated by the largest clique size. So typically what you'll do here is, you know, if your clique structure or factor structure is interesting enough, these will be small enough that you get a very significant gain relative to the combined space, right, of just all possible outputs, right? So a lot of the combinatorics, right, there might still be some combinatorics now left within each factor, but that will be much smaller than, you know, to talk about all possible outputs. So that means then that representation, right, is also finite, but it can in practice, right, be much smaller in the sense of number of parameters that you need than the representer theorem that we talked about yesterday, which would just say it's a sum over I, sum over all possible outputs, alpha IY or beta IY, what we have there yesterday, right? Now, of course, with the oracle-based approaches, right, if you look at them, all of them, we've tried to maintain sparseness and at the same time trade off sparseness and approximation quality, right? We would say, how many steps do I have to make in order to get an epsilon approximation? And we wanted that number to be small because that number was also related to the sparseness of our solution, right? So with the original representer theorem, if we look for approximate solutions, we might have also very drastic sparseness that is sufficient so that the solutions that we get, right, are much more compact than what the representer theorem would tell us. But this is also good because it's a much better starting point, right? We don't have like sparseness to come to the rescue in approximation because we know from the start that there's only much smaller number of variables, right? So I think that philosophically is of course different and is very interesting whenever that is possible to work with such a factorization. So you can then actually look at this also in the dual view, and it's really quite easy and very illuminating to kind of do that. So this is the dual that we've always been looking at. Some matrix Q, there's our alpha, quadratic part, linear part, the usual constraints. What you can see that what really matters, the reparametrization that you can actually do it directly of what the representer theorem tells you. You can just achieve by doing the following. You sum up all these alpha I, y variables for a given I and y, and the ones that you actually sum up are the ones where your output over that factor C attains a specific value z, right? So I look at all possible factors or cliques, the values that they can take, and I basically sum up all these alpha values dependent on, right, what cluster or factor I've chosen and what the value is, right? I can just kind of do that. And then of course, if I sum that for a given I and C over possible Z's, since Z's is the possible output space, the state space over for that factor indexed by C, it'll just add to 1, right? And you can also just see if you apply that summation to this expression here, since these guys add up to 1, right, according to this equality constraint, that's what you get, right? So what you effectively introduce here in this step are, you can think of as being like marginal probabilities, right? If these alphas in some sense correspond to a probability mass function over possible outputs for each index I, then this here actually corresponds to something like marginal probabilities over the factors, if you like, right? So mu I, z, z would basically be a probability for data point I, factor C, that is in a particular state, that set of variables is in a particular state. And now you can actually look at, basically apply this summation here to all the relevant parts in the objective. So I just do this for the loss part. You could similarly do it for the quadratic part, then it gets a little bit more messy. But basically just imagine that I do the same summation here over that part. So actually, if we assuming that this decomposition holds, right? So decomposition of the loss and also decomposition of our features that are the feature vectors that are absorbed in this Q. So for the loss function, for instance, the assumption then amounts to saying that that loss can be written as a sum of losses over for each factor, right? So basically we can go from here towards here, and then we can kind of add a summation over all possible states of that factor and put in like an indicator function here and regroup terms. And what you will get is basically the definition, you will recover the definition of our marginals here, and you will get this loss term that is only talking about this factor, how your prediction differs from the true value over the variables that are part of this factor. Okay? So instead of having a sum over I and y, you then have a sum over I, C, and z, right? Which is exactly what you want and what you had in the representer theorem. And you can do the same with this Q matrix. So this alpha Q transpose Q alpha term, you can also break that up. Do the summation, and then what you end up with is basically a new quadratic program. It looks like almost the same as before. You have again some matrix Q here that now is just defined differently, right? Instead of having an index over I, y pairs, you have one over I factor pairs. And you also have this linear part again and this quadratic part. But it is now a much lower dimensional problem because, right, the state space of all the marginals is much smaller than the joint state space that we've been talking about before, right? So that's cool. So are we done at that point? Well, unfortunately, there's one thing missing here, which is if you do this, you also need to be more careful about the constraints that now these mu variables need to fulfill. So clearly they need to be normalized, right? I mean, we've kind of done that already. We've seen that already here. The way we define them, they are actually automatically normalized. So kind of, you know, if the alphas were normalized, then according to that definition, these guys would also be normalized. So, but of course, once we throw away the alphas and work directly in the mu's, we need to enforce that constraint on the mu's. But that is very easy, right? We just know what these constraints are. For each clique and each training point, the sum of these mu variables for all possible state needs to add up to 1 so that it is a marginal probability. But the problem is that that is not enough. We also need mu to really be on the marginal polytope. So what that means is the mu variables that we have, we need to make sure that they correspond to really being marginals for some joint distribution, right? There needs to be some joint distribution that has these marginals. And if we just treat the mu's as free parameters in our optimization problem, then that might not be the case, right? We might actually end up with marginals that are inconsistent with each other because the factors can overlap, right? If the factors wouldn't overlap, that wouldn't be a problem, but the factors can overlap, right, in various ways. Like, I mean, this is the main problem of probabilistic inference in graphical models, right? That you have factors that, or cliques that overlap with other cliques. So, so the problem is that you still need to enforce that. And that is, of course, now, again, problem specific, but that can be a problem. And if you like, what we do here then, like, intuitively is that the objective, right? We break the objective really into these contributions that come from smaller parts, which is great, right? But we still need to maintain some kind of a global view. And in this representation, the global view kind of comes from enforcing the constraints on the local consistency of our marginals, okay? So to give you a specific example, if our factor graph is singly connected, so meaning, let's say, we just have a chain, right, of variables, and the factors that we form, for instance, are just pairs, right? So we would actually, all the factors would also just form a chain. Or there would be tree structure, or in general, singly connected factor graphs. Then the local consistency is relatively easy to achieve. We would basically have singleton and pairwise factors, and we would, for instance, say that if we take the marginals over the pairs, that if we marginalize out like one of the variables, we should get the same marginals over, let's say, the single variables, and things like that, right? So the types of things you would get from graphical models. So if we have a problem where our output variables are part of a factor graph, but it is a singly connected factor graph, then it would be sufficient to just add these constraints. So this problem of making sure that mu is on the marginal polytope basically amounts to just adding these constraints. And there's a small number of them, and then we're fine. Okay. In general, if we have more complicated dependency structures, let's say we do image segmentation and we have like an Ising lattice of where our variables are arranged and all the factors are, again, pairwise, all the neighboring variables, then that would not be singly connected, but they would be multiply connected, and then we couldn't do that. We could still add those, but then we would only get a relaxation of the real problem because we're missing some constraints. Okay, we know that these ones need to hold at any rate, but in graphs that wouldn't be singly connected, we need more than that. But it means maybe we can just work with this relaxation and things are fine. And that is actually what would be in the spirit of belief propagation methods and so on and so forth. And you can actually incorporate a lot of that wisdom into solving these structured prediction problems exactly at this point, right? By going from this global view into this factored view, introducing these new variables, right, that are now defined over your factors, and now use all the smartness that you can use maybe for relaxations, like the type of work that Martin Wainwright and others have been doing, and bring that in here to find maybe good relaxations of the marginal polytope for your problem. Okay, so there is that, and once you think about more in this factor graph or Markov network or graphical models framework, you might ask yourself, well, you know, maybe this all has also something to do with what would you do if you would start with maybe a probabilistic model from the start, right? Because we started with support vector machines as a motivation, introducing of margins, enforcing margin constraints, and somehow we ended up in a place where now we're talking about graphical models, a decomposition of the variables in our domain, and so on and so forth. So obviously it seems that there's also a connection to graphical models in particular if we have these decompositions. And so I want to use like the last part of my lecture to make that connection. So first of all, it should also be clear that this function f that we've defined, and typically we use this linear form, right, with a joint feature function, that we could of course also use it not just to define some compatibility score that we then maximize to find the right output, but also we can use it to define directly a probability distribution over outputs. So instead of just defining a deterministic output function that maximizes our f of x, y over y, we could just say, well, maybe we can just directly turn it into a probability, and we would just do it like this, right? You would do it as an exponential family type of model, as we will see later. So you could say, well, the conditional probability of an output given an input as determined by f is e to the whatever value of f, and then I have a normalizing constant that just makes sure. So this would just be a summation in the case that we looked at, the discrete case that we looked at. Okay, so of course if I would maximize that probability, then effectively I would just look for the maximum exponent here, which would just be the same as we had before, right? So if I made a deterministic choice of what the best output would be, I would just do it through maximization. But I have a bit more here, because here I have an actual probability distribution over output defined. So that could be nice. And indeed, if you look at this, you will see that things like generalized linear models, right, you can actually bring into that form where you have a particular sufficient statistics vector and canonical parameters. There's other things around non-parametric kernel models that let me just skip over that. So there's a lot of things that actually we can connect to that view. And in particular, what you might also be interested if you have this probabilistic view, right, would be to say, well, why should I optimize some margin-based criterion, right? I want to do something that is more like a likelihood-based approach, right? Or maybe a Bayesian approach to that. So, and indeed, this is what you can do here. So maybe what you would want to do instead of this approach that we pursued so far, you want to use a log loss function. Okay, so then what would your objective look like? You would basically say, look at the log probability under your model f of an output, an observed output for an observed input, right? You would add up these log probabilities for all training points that you've observed, right? So this would be your log likelihood. So the minus of that would be, I guess, the log likelihood. So this is our log loss. And then also you have some condition that say f comes from some reproducing kernel Hilbert space, which gives you some way of regularizing f. So in the finite dimensional case, you think of that as always being just a norm of some weight vector that defines f, right? So that then would look very similar to what we've been talked about, but it's now with a log loss instead of a hinge loss, right? that we've been using. And indeed, this is a problem that has been studied a lot, right, under the name of conditional random fields. And people there have used techniques like iterative scaling or various gradient-based method, conjugate gradient descent, and other methods in a series of early papers around that. All of those methods typically require you to compute expected statistics over these sufficient statistics vectors phi. Okay, so you need to be able to compute an expectation, given x, an expectation of psi under the random variable y, where the expectation is relative to your current model. And that just comes from, like, you know, I hope you've seen that before. When you have exponential models and you want to fit them, you need to compare your sample statistics with your expected statistics over your sufficient statistics vector. So that's a way that, right, alternatively to this structured SVM approach, that you can think about structured prediction in this conditional random field model. And I think it gets more interesting and more intricate to see, like, the similarity and the differences if you actually then also go and take what we had on the previous slide and derive dual formulation for that, for the log loss version. So this is the dual of this log linear model fitting criterion. And what you see, and I've kind of done it here by putting both now together, is if you do that, you get actually the same data dependency in this matrix Q here. So the quadratic term is actually the same. And you get, before you basically got a term that would be, right, this alpha I y, our dual variable, times whatever the loss is for the y that alpha I y stands for. And now what you get here is actually an entropy term. So you get a negative entropy in here, right? Of course, that's well known that, right, if you have like exponential family log linear models, and you look at the dual, then basically you get something like a maximum entropy style criterion, and that's also what you kind of recover here. So we are saying, which is actually the same quadratic part that we're trying to optimize, but here we would also like to maximize the entropy at the same time, whereas here we have a different linear part that relates to our specific loss function. Okay. So, so that means if basically we have two ways now to think about structured prediction, we could use the same model class F, the same feature functions psi. We can think of them as going through the support vector machine round and hinge laws, and we kind of arrive at this, and we've talked about possible ways of solving this already. Or we could think of this function f, these linear discriminants that we have of defining an actual probabilistic model and using more of a likelihood-based approach, a log loss-based approach, and we would end up here. And both would be viable ways of doing things, each having some advantages and some disadvantages. So once you're in that formulation, there's also now you might wonder whether you can also devise algorithms that actually work for this quadratic program, and also for this one here, for this optimization problem that involves an entropy term. And so there's also rich literature that has been developed on that. So my favorite method here is the exponentiated gradient descent algorithm that you could use basically for both of those. So the way that would work is basically it would update these alpha parameters from time step t to the next one by multiplying by some exponential of a gradient, the gradient of this objective exactly that we had here. So this is our H, right, is either this one or it's either that one, depending on which formulation we have. And you can actually sort out what that is. And basically you can see that all that requires you to do is to be able to compute some inner products of your current weight vector that you maintain in a primal parametrization with these feature vectors. And then you have your loss function there. And so then you can actually apply this. This is the formulation that you would get for the support vector machine case, and you could get a similar one also for the conditional random field case. And then finally, you can put it all together. If you actually have a factorization over your output space that you can use to reduce the dimensionality, because here, right, this is nice, but basically that doesn't tell you anything about sparseness, right? So if that number of variables is much too large to explicitly use, which is often the case in our case of large output spaces, then right, you cannot naively apply this. So obviously you would also like to use the idea that comes from factorization and working with marginals. So, and basically you can do this. You can again simply look at this equation here. There's a proportionality in there, kind of, that you need to renormalize things. But if you would sum again the left and the right-hand side, it's kind of just what I've done here, and you don't have to go through the steps, but just to show that it's really that simple. You basically get an update equation that tells you, well, this marginal at time step t plus 1 should be equal to the previous marginal plus some exponential update rule that now contains things that just have to do with this specific factor c, okay? So you see that here again, you recover something that now only depends on properties that have to do with a specific factor that you've chosen, okay? So then you can also apply this exponentiated gradient descent algorithm, be it for the log loss case or for the support vector machine case, by reducing the dimension, first reducing the dimensionality through factorization, and then using this general scheme for incremental updates. And it actually turns out, and I found that quite surprising, that for the log loss, you have like one of the key advantages that you're getting specifically with this method is that the convergence rate that you're getting can be much faster than just 1 over epsilon. It can actually be log of 1 over epsilon, which can be a huge advantage in practice for scaling this up. Okay, so let me come to my last slide here, and then we can maybe enter more in a discussion stage. So what have we seen in these two lectures? So one is, so I started with trying to generalize support vector machines to deal with much more than just binary output or regression, to deal with structured outputs. And we wanted to do this in a scalable manner from the start. We've looked a lot at this oracle-based architecture, where we've kind of came up with a formulation of our learning problem and some algorithms that would need this oracle as a black box to call it, which was nice from a software engineering perspective because you can separate the two. And we looked at different things of how to do this, subgradient, cutting plane, and so on and so forth, Frank Wolfe. We looked at features and loss functions and like what flexibility that would give us to model like a wide range of problems that could all be brought into the same computational framework and modeling framework. We saw also that all across the board, if we want, we can use kernels. And there's very nice ways of defining these kernels and computing with these kernels. Again, we talked a lot about algorithms. And then also, if there is a way that your output can be decomposed naturally into, let's say, smaller cardinality variables that form certain factors where the dependencies are limited to within like smaller sets of variables, then you could use a lot of the machinery from approximate probabilistic inference, graphical models, and so on and so forth to help you, in particular, if you look at this dual view of the problem and use that to tackle it. There's, of course, this relation that I tried to point out to conditional random fields. In particular, if we look at like this case where we have a decomposition. There's a question, of course, with conditional random field sparseness is always an issue. So maybe we can talk about that in the discussion, what also the advantages maybe of the hinge loss approach are. And in terms of applications, we didn't really talk much about it here, but I think there still is an increasing number of applications where these techniques will become relevant. So I think it's also worth continuing, like making an investment into the development of better models and better algorithms in that domain. Okay, so that's it from my side today. Thank you.
Okay, questions? If there are no questions here yet, maybe I can start with one. So you showed some quite complicated models to learn quite complicated objects. Well, actually, not well. Models to learn very, very complicated classes of objects. Maybe to make a connection to the next talk by Ingo Steinwald. Are there also some results known about sort of the identifiability of these models, or the sort of some consistency results for these kind of predictors?
Yeah, I think theoretically the support vector machine approach, but Ingo might know that better. But they are not; these are not consistent estimators in a statistical sense, right? So if you're a fan of theory and believe in that, then you would probably frown on these methods. And for the log loss case, that is the case, though. Mm-hmm. On the other hand, yeah. They've been used for lots and lots of practical problems, and then you can also, of course, wonder about how important that really is. But I think that would be interesting to understand, like from a theoretical side, also, what these differences are. So for me, like I'm always coming more from a computational side. There is just a huge advantage of the sparseness in computation, and also once you've learned the model in whatever you do afterwards, right, in applying that model in a scalable manner. So I think in that sense, this hinge loss-based approach is quite interesting. Yeah, but it has this theoretical worrisome flaw.
Are there any questions in the observation lounge? Hopefully well-filled observation lounge.
Yeah. Yes, there's one question here.
Hi. So for the structured prediction, they are basically SVM struct and conditional random fields, like two methods to choose from. So can you briefly tell us what is the pros and the cons of both approaches, and for some applications, if you know their properties, is there any heuristics which kind of method that we could choose? Thanks.
Yeah, sure. So yeah, so what are your so what are the possibilities, right? So if you just look at the primal version, I just write down, I have some Markov random field, and I say, well, these are my output variables, and now I want to actually optimize like a conditional log likelihood criterion and have some regularization. Right? You could use gradient-based approaches, and you could basically solve it, and maybe that would be fine. For the support vector machine case, right, we've talked about a number of approaches that you could be using there. Now, in order to compute, right, the gradients for the CRFs, as I tried to just mentioned briefly, right, you need to be able to compute certain expectations, and for the SVM part, you need to be able to compute these oracles, these separation oracles. So one question is, for instance, are there cases where it is harder to compute that expectation relative to the maximization that you have to do for the oracle? There's some cases where that is the case. So that's one case where you might want to favor the SVM-based approach over the other one. Other than that, if we just look at the primal parameterization, it's a little bit like, do you favor SVMs over logistic regression or things like that? Because that's kind of what these two approaches kind of try to generalize. If you look at the dual, then I think things are somewhat different, because you can, with the support vector machine generalization, I think, in my view, also practically, you can get, like what I just said before also, you can get a lot of sparseness in the representation for an approximate solution, where usually you're anyway in practice okay with some tolerance and some approximation. And it's not so clear how to obtain this with log linear models. The sparseness is not kind of necessarily built in the same way. So you can try to add some regularization that potentially does that, or there have also been attempts to, in the dual by Michael Collins and others, of actually selecting variables on the fly so that you have sparseness through some variable selection process. That, but I think that is a major question for me, where I see then advantages of the SVM approach. And if they decompose nicely and you get a very compact parametrization, then sparseness is less of an issue, and then I would say I would probably favor a CRF-based approach, because I can just work with represent all the parameters that I need explicitly. So I think it's somewhat to be determined. Oh, and the other thing I should also say, that I think in the support vector machine case, you can much more directly also integrate the loss function that you want into the system through this margin rescaling or slack rescaling way that we've done it. I think, maybe some of you know more about how to do that in a clever way with CRFs, but I think that's also an advantage of SVMs.